Hello everyone! In today's lesson, we'll look at the inverse of trigonometric functions, which will give us necessary tools to solve trigonometric equations in the upcoming lessons. Let's think back to the sine function. We know sine of x takes in the measure of an angle in radians and outputs the y-coordinate of the point at which the angle's terminal side intersects the unit circle. Our goal right now will be to find a function that does the exact inverse, takes in the y-coordinate of a point on the unit circle, and outputs the corresponding angle measure in radians. To figure this out, let's analyze the graph of sine of x. How do we go about finding the inverse of a function? Remember, we first need to make sure the function is invertible. In Unit 1, we learned that a function is invertible if it is 1-to-1, which happens when the function passes the horizontal line test. That is, when any given horizontal line intersects the graph at most once. Is that the case for the sine function? Definitely not. Does that mean we can't find its inverse? In Unit 1, we also learned we can make a function invertible by restricting its domain, so that we only grab an interval over which the function does pass the horizontal line test. As is, the sine function has a domain of -infinity to infinity and a range of -1 to 1 inclusive. On your own, analyze the graph and find a domain restriction over which the sine function would be invertible. Pause the video now. The sine function repeats itself infinitely, so there are infinitely many domain restrictions that would work. For example, the intervals -3 pi over 2 to -pi over 2, -pi over 2 to pi over 2, and pi over 2 to 3 pi over 2 all grab portions of the graph that pass the horizontal line test. However, for the sake of simplicity and convenience, the standard domain restriction we use for the inverse of sine is -pi over 2 to pi over 2. Slicing out only this portion of the graph, the sine function now passes the horizontal line test and is therefore now invertible. This restricted sine function now has domain -pi over 2 to pi over 2, but it keeps its range of -1 to 1. Now let's find the inverse. Do you remember how we can graph the inverse of a function? Inverses are reflections of each other over the line y equals x. So to get the graph of inverse sine, we just reflect our restricted graph over y equals x. And ta-da! We call this function inverse sine, which we notate using the -1 superscript. Inverse sine is also often called arc sine, so we'll be using both these names interchangeably. What are the domain and range of this function? Well, remember, we can just look at the domain and range of the original function and switch them up. Therefore, inverse sine has a domain of -1 to 1 inclusive and a range of -pi over 2 to pi over 2 inclusive. Let's see how our new inverse sine function works. Here we have two inverse trigonometric expressions we need to evaluate with the unit circle. Make sure you have your unit circle reference sheet with you, as you will need it throughout this entire lesson. Let's start with inverse sine of 1/2. First off, what is the meaning of this expression? The inverse sine function will do the exact inverse of the sine function. It will take in a sine value, or y-coordinate of a point on the unit circle, and output the corresponding angle measure in radians. However, it has a very specific domain and range. The sine values taken in must always be between -1 and +1 inclusive, and the angle measures outputted will always be between -pi over 2 to pi over 2 inclusive. On the unit circle, remember negative angles are those measured clockwise, so negative pi over 2 falls on the same place as 3 pi over 2, and the angles in the fourth quadrant can all be seen as simply the negative, reflected versions of the angles in the first quadrant. Therefore, the angles that inverse sine considers fall exclusively on the right half of the unit circle, from negative pi over 2 right at the bottom, all the way to pi over 2 right at the top. What this expression is asking then is what angle measure in radians in the interval negative pi over 2 to pi over 2 corresponds to a y-coordinate of 1/2 on the unit circle. Since inverse sine is a function, there should be and there is only one possible answer: pi over 6. Now let's evaluate arc sine of negative square root of 3 over 2. Try it out on your own. Make sure you have your unit circle reference sheet with you. Pause the video now. This expression represents the radian angle measure in the interval negative pi over 2 to pi over 2 that has a sine value of negative square root of 3 over 2. That would be negative pi over 3. Here's a second example. This time we'll need help from our calculator though, since we're given inputs that are not sine values of special angles on the unit circle. Before we input these in the calculator, let's visualize what these expressions are asking for. Inverse sine of 2/3 is asking of us for the radian measure of the angle in the right half of the unit circle that gives a sine value of 2/3, which we predict should be a bit less than pi over 4, which is approximately 0.785 radians. Similarly, arc sine of negative 0.4 asks for the radian measure of the angle that gives a sine of negative 0.4, which puts us in the fourth quadrant, and the corresponding angle should end up a bit above negative pi over 6. Now that we know what we're looking for, use a scientific or graphing calculator to estimate these inverse sine values to 4 decimal places. Calculators will often use the -1 superscript notation for inverse trig functions, so make sure to look for those. Also, make sure your calculator is set to radian mode. Otherwise, it will give you the answers in degrees. Pause the video and try it out now. Inverse sine of 2/3 is approximately equal to 0.7297, and arc sine of negative 0.4 is approximately equal to negative 0.4115. Both of these answers make sense with where we expected these angles to lie in our unit circle. Now let's find the inverses of cosine and tangent. Here are the graphs of the cosine and tangent functions. Are these functions invertible? Once again, these functions don't pass the horizontal line test since horizontal lines intersect them infinitely many times. On your own, analyze these graphs and find domain restrictions for which the cosine and tangent functions become invertible. Pause the video now. Even though there are infinitely many domain restrictions that would work, the convention is to grab the interval 0 to pi, inclusive, for cosine, and the interval negative pi over 2 to pi over 2, non-inclusive, for tangent. With these domain restrictions, cosine of x and tangent of x are now invertible. Here are their new domains and ranges. Notice how these restricted domains keep their original ranges intact. Now let's find the inverses. Reflecting these graphs over the line y equals x, we get the graph of inverse cosine, also known as arc cosine, and the graph of inverse tangent, also known as arctangent. Notice how the vertical asymptotes of the tangent function become horizontal asymptotes of the inverse tangent function at y equals pi over 2 and y equals negative pi over 2. On your own, state the domain and range for inverse cosine and for inverse tangent. Pause the video to do so now. We take the domain and range of the restricted cosine and tangent functions and switch the domains with the ranges. Inverse cosine ends up with a domain of -1 to 1 inclusive and a range of 0 to pi inclusive. An inverse tangent ends up with a domain of -infinity to infinity and a range of -pi/2 to pi/2 non-inclusive. We can also see how our graphs confirm these domains and ranges. Let's wrap up our lesson with a final example. We'll find the exact value of these expressions if they come from special angles in the unit circle, and if not, we'll use a calculator and approximate them to 4 decimal places. To evaluate these expressions, we need to have in mind the domain and range of inverse cosine and inverse tangent. The inverse cosine expressions will take in the x-coordinate of a point on the unit circle and output an angle only in the range 0 to pi, which means the angles will come exclusively from the top half of the unit circle. The inverse tangent expressions will take in a tangent value, which is the result of dividing the y-coordinate by the x-coordinate of a point on the unit circle and output an angle only in the range -pi/2 to pi/2, which means these angles will come exclusively from the right half of the unit circle, just like inverse sine. Having these things in mind, try to evaluate these expressions on your own. Pause the video and try them out now. Let's check your work. Looking at the top half of the unit circle from 0 to pi, we see 3 pi/4 has a cosine value, or x-coordinate, of -√2/2, which means inverse cosine of -√2/2 is 3 pi/4. To evaluate the second expression, we should first evaluate the inside expression tangent of 5 pi/4, which we can do by dividing the y-coordinate by the x-coordinate of the corresponding point, which results in 1. Our original expression is therefore equal to arctangent of 1. The range of inverse tangent directs us to the right half of the unit circle, particularly from -pi/2 to pi/2. There, we locate the angle that has a tangent of 1, which means the y-coordinate over the x-coordinate for the point associated with it must equal 1. This is true of pi/4 because the x and y coordinates are the same. Therefore, arctangent of 1 is pi/4. For the third expression, we use a calculator since -3/4 is not the tangent of any of our special angles, and we get approximately -0.6435. Lastly, let's look at arc cosine of 2. You might have tried to put this one in the calculator and noticed that you got undefined. Why does this happen? Well, this expression has a huge problem, considering what the domain of inverse cosine is. Inverse cosine only accepts inputs in the interval -1 to 1 inclusive, which makes sense because those are the rightmost and leftmost x-coordinates on the unit circle. Since 2 is outside this domain, arc cosine of 2 is undefined. Today we discovered 3 new functions: inverse sine, inverse cosine, and inverse tangent, and we learned their corresponding domains and ranges. We evaluated these functions using the unit circle and the calculator. In our next lesson, these functions will help us solve trigonometric equations. Once you've finished your guided notes, complete the additional practice. After that, make sure to complete the online practice. See you next time. Hey.